And what we're going to be talking about next is really about controlling autonomous swarms of devices, of robotic systems. So this should be interesting. Hopefully you guys will find some interesting things here. So some of the key points to understand about current autonomous system management is that it's very difficult to do right now. In fact, we kind of overdo it. In order to control a drone, we have like 1 to 5 pilots and 100 analysts who all look at this drone's feedback and try to control not only the drone, but what it's supposed to be doing, what it's seen, and manage the kind of input from it. So this control paradigm, I don't know if it's obvious or not, but this control paradigm doesn't scale, right? It has a huge training cost. You can't expect these drone pilots to really stay around for 20 years, and they're not. They're swapping out pretty quickly. And then you have to train the next generation, the next generation, the next generation, and you have this high training cost for every drone you pretty much manage, which just means that we don't utilize our full drone fleet, really. And we think this is a problem. We think this is not something we can keep going with, right? So another problem really with a centralized control station kind of design that we have right now is it doesn't scale either. It's also failure prone. An enemy that is in any way technologically advanced can just take out the control station and your whole drone fleet will kind of be out of commission. So we want to look at how to get away from this centralized control paradigm and move more into a decentralized distributed process. Another thing that we look at in this project is the fact that a lot of the distributed artificial intelligence that we see in academia is really preset. It's a one-off. It's sort of like we mentioned earlier papers, that academic papers, they tend to be a one-off system where it's just showing a proof of concept and it's not meant to change or to really adapt to a mission. And for DoD or any kind of really a real system, you really want it to adapt to the environment, to change and to become a better system. And so what we've done this year, and really this is kind of the end of a 3-year project, is focus on scalability, also bringing simulated AI into reality. This is a huge problem. I was at the AFRL TIM about 4 weeks ago for autonomy, and all of their projects were in simulation. None of them were actually real. And so anybody will tell you it's really difficult to take this distributed AI concept from this computer simulation and bring it into the real world. And so we've got some things we've done to help people out with that. Another thing that's important to get any kind of distributed autonomy in place is the trust of a distributed system. And in order to have trust of these kind of autonomous systems, you need to have a lot better predictable control of the UAS logic, its threading, its sensors and actuators, and how it interacts with other agents. Okay, and I use agents because I'm an AI guy, and that's just how we kind of characterize these autonomous systems. Another thing that's interesting about this work is that we provide everything we do as open source. So you can download this as a BSD license, you can tweak it, you can play with it. It works with other things like ROS and various other things. And that kind of leads into this next slide. There are other robotic control infrastructures out there. There are other middlewares that you can play with right now out there. There are things like the robot operating system, what's called ROS commonly. Google's taken over the development of quite a bit of that. And then there's Stage Player, which is more of an academic kind of look at this. Am I moving in and out of people's hearing? It sounds like things are echoing a little differently. Can you guys hear me okay? Okay. These things have a lot of problems with them. They're not really meant for disconnected environments. They're not meant for wireless environments. They're not meant for the real world in a lot of cases. A lot of cases, these were developed as academic middlewares to help you be able to do the next generation of robotics, and that's fine. It gives us a lot of capabilities. But when you move them into the field, when you start using wireless communications with a distributed agent system, they just break down. They don't work, and they don't scale. Talking with a lot of people at the Robotics Institute at Carnegie Mellon, a lot of these things will not go past a few dozen, maybe, that you can control, and really they need to be centralized. They claim they can be distributed, but they're using protocols like TCP, which means that, I don't know if you guys have ever been in dorm life, but you've ever had your roommate downloading a whole bunch of stuff. TCP is really good about hogging a connection for one thing and not letting anybody else talk. So this happens a lot in multi-agent systems. You have to look out for this. Another thing that ROS and Stage Player don't do is they give you no consistency guarantees. They give you no quality of service to really be able to verify or enforce any part of your multi-agent system is cooperating with what your design is. They really have a lot of emergent behaviors that happen with them. Another thing that we bring to the table is this concept of programming with containers. They're really like variables that you use in the language of your choice, Java, C++, Python, instead of working with sockets and message-based stuff. You really look at a container, you program the way your logic in this algorithm that you read in a paper works, and this is how you program your distributed artificial intelligence. And the last thing we provide here is built-in support for bringing your simulation to the real world. And I'll show you a video of some things that we did for students coming up. So just going over some of these challenges and how we kind of approach these and what we did, one of the main things, and it's something that for most people boggles their mind, is we stopped using TCP, we stopped even using reliable communication because they're all blocking, and once you get out of disconnection for 5 or 10 minutes, you have a queue-based system that builds up, and you try to deliver the oldest messages even if you have enough queue for it, and if you don't, you might just crash your application. So what we do is we focus more on unreliable communication and resending information that's very important, like your location, where your intent is as a robot. And so you get the latest stuff, which is more important to the distributed agent system anyway, not what they did 5 minutes ago, which you never heard about because a mountain was in between you, something like that. So this has worked out pretty well for outdoor distributed autonomy. We also minimize blocking behaviors. In fact, we try to eradicate them altogether, and we provide O of 1 access to knowledge within the system so that you can get this quickly. It's not log of in access, which you see in a lot of knowledge bases, or even O of n access. And we add scalable read threads. We control the publish and receive rates. We also add this controllable AI execution via MAPE constructs. This is an IBM concept. It stands for monitor, analyze, plan, execute. It just kind of gives you a way of predicting and understanding how your AI is going to execute. And then that's how we kind of address this challenge. Another challenge that we deal with working with a company called Platypus, it's a CMU-based company under Paul Sherry. He's a professor over at the Robotics Institute, is that we've provided 2 key things. One of them is the ability to specify pose information. This is things in your reference frame. So you can basically take a Cartesian grid system that you do in simulation, which is the way most people do it with like an origin of 0, 0, and they move 1, 2, 3, 4, whatever. And we can actually map this built in to GPS or any other kind of coordinate system you want to use, whether it's cylindrical, whether it's a satellite-based communication reference frame or something like that. It's built in, inherent, and all you have to do is set your reference frame to something different. It does it for you. Another thing is that we only use simulators that provide real-world physics kind of capabilities. In fact, what we're using right now for a boat platform for the Platypus LLC company is so accurate, they designed their entire PID controller system based on the simulator, not the real-world environment. So everything about the currents, everything else is worked out in the real world, that this has actually modeled their proportional integral derivative controller for autonomous ship control with our simulator. Another thing that we'll talk more about this tomorrow during the DART talk is that we want to make this trustworthy. We want to make verification of distributed autonomy possible. So what we did was we really focused on the internals of middleware itself, on the threading models, on the networking layers, and guaranteed consistency. How is knowledge received? How can you prove something about this, right? And we've done a lot with the DART project to help kind of enforce distributed autonomy and understand what is possible, what's not. We presented a lot of algorithms that use things like synchronous models of computation, which are essentially barriers among distributed agents so that you know that they hold the formation correctly, that they avoid collisions, that they do things like that. So you can actually, you can prove properties about a system and its mission that's ongoing because they use a better model of computation that's able to work in the outdoors. Another thing that we've added is we've added the ability to change artificial intelligence as a mission changes. So one of the things we look at is kind of these harbor scenarios for Platypus because they have these boats, they're trying to detect pollution or biohazards or maybe even nuclear weapons or something like that. And if you're running a straight up coverage, a serpentine pattern or whatever you're doing as a distributed AI, and you find this hazardous material, are you supposed to just keep going as if you hadn't found it? I mean, is that the right way to go about this? Probably not. You probably wanted to divert some of your swarm, you want to contact human operators, and you want to tell them, look, we found something serious. We think you need to look into this. You need to isolate this entire part of the harbor, or you need to contact the people who are polluting the harbor, like the company that's next to you, that kind of thing. So it has a lot of different things. And so what we did was we created this algorithm factory infrastructure that allows you to bind new algorithms to commands. Basically, you could say change formation, change the mission, do a coverage, something like that. And this is able to work with both C++, Java, or Python code. And you could basically do this at runtime and get something more interesting. For scalability, with Platypus, they really only run at a 5 hertz publish rate per boat, which means that we can basically, we know we can scale even with a reduced ARM instruction set and this low-powered ARM processor, that we can scale to about 1,700 boats collaborating pretty effectively. This is a cluster you can see in my office if you're ever going by. It looks like Christmas when it's lit up. But essentially, we know that when they publish at the rate that they're doing in the real world, we can get about 1,700. When they're doing a higher rate, if they were actually to want to increase the rate and start doing more information, publish more frequently, we could get it to about 280 boats working together. So as far as bringing simulation to reality, you can see a video is just going to play as I'm going here. This is just simple formations that maintain their formation as they're going outdoors. They have disconnects going on the water. If you've ever done robotics on water, You have things like multipathing on the water that cause temporary loss of communication between the boats, between the user operator and the boat, whatever like this. And even though they're having these problems with the communication, they're able to maintain their formation, they're able to correct things as they go, they're able to rebroadcast information between the swarm so that they can all get the messages that are important for their synchronous model of computation. This involved about 100,000 lines of code in C++ being fully ported to Android because they wanted to use Android phones for their center package. It was a lot more work than we anticipated, but we did get it done. We do have deployments of these boats in various countries from North America, South America, the Middle East, and Europe, including 20 boats deployed in Qatar for the CMU Qatar campus. Another really interesting project that we're working on right now is the Keck Institute for Space Studies Multiplanetary Smart Tile project. This involves trying to deploy thousands of smart tiles in space for energy harvesting, for power beaming, for localization of spacecraft going through asteroid belts, and it's really trying to set the stage for Mars colonization and trying to get things in place for the power requirements, for hydrolysis of splitting the packed Mars water into oxygen and fuel. And we're working on that proposal right now with JPL, Caltech, and AFRL Space Branch. But Madar and GAMS are actually the knowledge reasoning and group autonomy framework for the tile swarm as the proposal is being written right now. And we've created a bunch of simulations and code that show how the smart tiles might move to create solar panels, how you might be able to build structures, and how we can do outreach to the community, like high schools, to let them build their own high school's name and stuff like that with the tiles and be able to see them from space. So a lot of cool stuff going on there. The way Platypus currently uses this is they have our two middleware infrastructures called GAMS and Madara on their boats and on the user interfaces to communicate with the boats. And it uses UDP between them, and you can see just an overview of how that goes. As far as future work goes, we're hoping to do a bunch of deployments of 20 plus boats in Qatar coming up in November, December. And we want to be able to split the boat into competitive groups that actually compete against each other for real world DoD-like things. Like they might disrupt each other, they might try to kill each other virtually, hopefully, because I really don't want to pay for the replacements. But it should be interesting for DoD problem sets because in the real world we do have to deal with adversaries. Not only the environment being adversarial, but actual adversarial agents going against us. And so this involves extending the GAMS middleware with adversarial models. It involves creating algorithms that are adversarial aware and extending this pose system to have intrinsic rotations and translations for actuators on the boat itself. So I'm running out of time. I'm actually out of time. I know we're coming up on a break, but we're okay? All right, so I just want to point a couple of things out here. You can actually go to these URLs to see the open source that we have available for all these. All this is available. All the algorithms are available for you guys to download and try out in simulation. And if you want to have a robotic system that does this, we can certainly talk about it. And some of this stuff, also the precursor to Dart that you'll hear about tomorrow, is also linked here. It shows you how to use the synchronous model computation and a verification of a distributed system. And you can see a lot of our colleagues here from CMU and Vanderbilt. And I'll just skip over some things to back up real quickly. If you're wanting to play around with the open source repository, here are some of the algorithms. And again, these are all available. Palmer's got the slides for you, I'm sure. And you can see and play with each of these things with formation-based movements, synchronized formations, convoy shielding, things of that nature. Some of these DoD-type missions that we have encoded, along with all the platforms. We do work with ROS. We do work with other kinds of middleware. We're not stingy on that kind of front, so we can talk more about that if you guys are interested.